Welcome back to Intermediate Algebra. Today, 6.1, rational exponents. So we are moving into roots, square roots, cube roots, that kind of stuff. And to do that, we're going to also look at some exponents. But let's start by looking at some roots. We're going to start with some nice ones that you should be fairly familiar with. And then on the next board, we'll get some little bit bigger ones. So the first one we have, this little sign, the square root of x, where x has to be greater than or equal to 0. You can't take the square root of a negative until later when you can, and it gets really interesting. Anyway, that's called the positive square root of x. So we call it a square root because it is such that if you take that square root of x and you square it, you get just the x on the inside. And I have an example down here, which is probably the best, much better way to explain it. The square root of 9 is equal to 3. And we know that it's 3 because 3 to the second gets you back to that 9 that was on the inside. So the square root is such that once you find it, if you square it, you get the thing that was on the inside. So we also have what's called a negative square root of x. And again, x still has to be greater than or equal to 0. And for a negative square root, it works the same way. If you square that whole thing, you do still get the thing on the inside. And this works because if you think about 9, right? I have this example down here with the square root of 9. 3 to the second power is certainly 9, but it's also true that negative 3 raised to the second power is 9. So there are two distinct answers for what the square root of 9 is. And so we distinguish them by calling one the positive square root and one the negative square root. And this will be true anytime we have an even square root, and we're going to see those here in just a minute. It won't be true for odd square roots, and we'll see that here in a minute too. So let me get a new board. All right, so let's look at the higher roots. We have a cube root, which is the third root of x. So we put this little 3 here, or on the next one for the fourth root, the little 4 up there. That number is what's called an index. All that number is it's telling us which root we're looking at. And so in other words, it's telling us what power you would have to raise that thing to just get the inside. So remember, we had the square root of 9. On that, we didn't put the 2. We don't usually write the index when it's a square root. In fact, we never do, ever. But we do with these. So for instance, if I wanted to find the fifth root of 32, this is just saying, what number do I have to raise to the fifth power to get 32? And in this case, the answer is 2. If you check my work, you'll find that 2 raised to the fifth power is 32. Notice that the index disappears along with the radical. Once we find that root, the answer is just 2. But we know that it's 2 because if we check, 2 to the fifth does give us 32. A couple of other notes. For even roots, so where n is an even number here for the index, x has to be greater than or equal to 0. So for example, the fourth root of negative 16. It is impossible to find a number that you can raise to the fourth power and get a negative. Okay, you can kind of try and think this through a little bit. The fourth root of positive 16 would just be 2, right? So 4 2's multiplied together makes 16. But with negative 16, you can't do 4 negative 2's because you're still going to get a positive 16 out of that. So for now, this does not exist. And note, I did put for now. We will see later on. We'll go explore the weird thing called imaginary and complex numbers, but not right now. So for right now, we're going to say that those don't exist, but they will later. So hang on to that. Anyway, but for odd roots, that doesn't matter. You can take the odd root of a negative because, for instance, if we had, say, the third root of negative 8, that is equal to negative 2, because if you multiply 3 negative 2's together, you will get a negative 8. So odd indices, you can do negatives. Even indices right now, you cannot. All right, let's get some more on the board. Okay, so as we continue into our study of roots, the reason we're doing this section called rational exponents is because it turns out we actually have a definition of roots and rational exponents that connects the two things. And that's going to be useful because we have a ton of properties for exponents, and we're going to then be able to use them to work with roots. And so we're just going to lay the groundwork for that here, and we'll see that more as we go through the rest of this chapter. But we're just going to lay the groundwork for that here, and we'll see a few examples of how we can use that. So our definition is just this. x to the 1 over nth power, so a reciprocal of n, is equal to the nth root of x. So whatever the index is on your radical, it's the same as having x raised to the 1 over that power. And so, like I said, we're going to look at these properties of exponents that hopefully you already know. If you don't, you really should go back and review them. But anyway, here we go. The first one, a to the m times a to the n. If you multiply two things with the same base, you can add the exponents. If you raise a base to 2 powers, you can multiply the exponents. If you have multiplication, now notice I have one for multiplication and one with division. I don't have addition and subtraction in there. If I do that, I can take the power to both pieces, so a to the m times b to the m. A negative exponent makes a reciprocal, so a to the negative m is 1 over a to the positive m power. If I have division on the inside, I can split the exponent again, a to the m over b to the m. And if I have division, then I subtract the exponents. So a to the m over a to the n is a to the b minus n. And for all of these except for numbers 3 and 5, the bases have to match. On 3 and 5, we're specifically working with multiplication of two bases on the inside or division of two bases on the inside. Everything else, the bases have to match. So let's take advantage of this and see what we can do. All right, so we have two examples here on the board, and I'm definitely standing in front of one. I'll let you see it here in just a second. But what we want to do is we just want to simplify these roots as much as we can. So here I have the third root, the cube root, if you will, of x to the 9th, y to the 12th, z to the 15th. So I start by rewriting my radical, my third root, as a 1/3 power, right? We have this connection between a root and the reciprocal of an exponent. And once I have that, I'm going to use the rules for exponents to first take this 1/3 to all three parts. So you'll see that I wrote it as x to the 9th to the 1/3, y to the 12th to the 1/3, and z to the 15th to the 1/3. I then multiplied my exponents together to get 9 over 3, 12 over 3, and 15 over 3, which reduced very nicely to 3, 4, and 5. All of that is a lot of work. Turns out, at least for now, there's a really awesome shortcut. Notice what ended up happening. We ended up taking the exponents on the inside and dividing them all by the index. And this is going to work really nice, especially if the division comes out even. In the next section, we'll see what happens if the division doesn't come out even. But if the division comes out even, really all you're doing is dividing those exponents by the index, right? 9 divided by 3, 12 divided by 3, 15 divided by 3 gives us our answer. And that's pretty nice. Now, why did I go through all that work to show you that we just ended up dividing? Well, because we'd like you to know that it actually comes from somewhere, that we didn't just magically make this up, that there is a process that we go through to have these rules that work for us and these shortcuts that are super nice. But yeah, basically, if your exponents are all divisible by the index, go ahead and divide the index. But what happens if you have a number on the inside and not just letters with exponents? So here I have the 5th root of 32 x to the 5th and y to the 20th. Now, if I left the 32 out, it's pretty easy to do the division again, right? 5 divided by 5 is 1, and 20 divided by 5 is 4, so x to the 1st, y to the 4th, no big deal. But what do we do with that 32? Well, we're going to do the same thing with the 32 that we would do with anything else. So you'll see here I broke it up with and made everything to the 1/5 power. I just need 32 to the 1/5 power. But again, that's the same as just the 5th root of 32. And the 5th root of 32 is 2. And so we get 2x to the 1st, y to the 4th. Of course, since we don't usually write that first power, you could just have 2x and then y to the 4th. Now, your calculator will do these bigger roots. I encourage you to figure out how. Some of you have a button on your calculator that will let you do any root that you want. Some of you will have to type in some other stuff. I highly recommend, if you have a calculator, if you're seeing me in class, you can ask, and I'll show you how to use your calculator. If you're not seeing me in class, look up your calculator on YouTube. I promise, if you look it up and say, how do I find the third root or something like that, you can find it on YouTube, and it'll tell you how to do it. All right, so there's those two examples. We have a little bit more here. Okay, last but not least, we have what's called the rational exponent theorem. Sorry, I had to look. If a is greater than or equal to 0, so if your base is positive, that's always important, a to the m over n power is the same as a to the 1 over n, so the nth root of a, then raised to the mth power, or do the power first and then take that root. Those will all be equivalent. So how could we use that? Well, let's find 125 to the 4/3 power. I don't really want to do the 4 on top first. That 125 to the 4th power is going to be very big. I can, however, find 125, the 3rd root of 125. It's going to end up being 5 pretty nicely. So I can do that one, and I've been doing this forever, so I can actually do that in my head, but I'm weird that way. So 125 to the 1/3 power. The 3rd root of 125 is 5, and then 5 to the 4th works out very nicely to be 625. So basically, we can take a fraction exponent like that and treat it as 2 parts, as a power and a root, and sometimes that makes it easier for us to solve them. So there you go. Have a great day.